Hi, I'm Rob Milner with FLIR Systems. I'm a Global Business Development Director, and today I will be helping you to understand how to use our FLIR thermal cameras to improve your plant safety and productivity while getting time back to perform maintenance. Let's begin with some basic infrared imaging theory for those who have not taken a formal Level 1 thermography training course. In this video, we will quickly review key concepts from the Infrared Training Center Level 1 thermography course. The Ford principle: focus, range, and distance. Emissivity, reflectivity, and transmissivity. Direct versus indirect temperature measurements. Effect of fans on temperature measurement. And why equipment needs to be running while being inspected. Let's begin with how an infrared camera works. Thermal cameras convert invisible heat wavelengths of light into something that we can see and measure. These light waves are focused onto a special kind of detector called a microbolometer, which is similar in some ways to a regular digital camera in that it is made up of an array of detector pixels. The camera electronics then calculate temperature values for each pixel, and the result is displayed as an image. There are three things the thermographer must do that cannot be changed after the image has been saved. We often refer to this as the Ford principle. F is for focus. The target must be in focus and without image blur when the image is captured. Otherwise, you will not have a good understanding of what the image is telling you, and your temperature measurements will be lower than in reality. R is for range. The camera must be set to the correct temperature range. T-Series cameras have 2 or 3 temperature ranges. For most applications, the lowest temperature range is the proper one to use. D is for distance. You cannot change how far you stood from your target when you save the image, so you must ensure you are standing an appropriate distance from the target in order to have enough pixels covering the target you need to measure. Let's look at a real issue with a known temperature of 40 degrees C. When we are too far away, the object size in the image is less than the width of a pixel. That means the pixel is not fully illuminated, and as a result measures a value much lower than 40 degrees C. When we get closer, the measurement improves. Now the object almost covers a full pixel, so we read a value that is closer to the actual temperature. Finally, when we get close enough so that the object is larger than a pixel, now we can read the actual temperature of the target. Emissivity, reflectivity, and transmissivity. The camera is gathering heat energy in the form of light wavelengths from 7.5 to 14 microns and focusing that light onto a detector. The light being gathered is either being emitted by an object, reflected off the object, or transmitted through the object. Emissivity plus reflectivity plus transmissivity equals 1. Most objects are not transmissive, so the energy is either emitted or reflected in most instances. Typically, rubber, plastics, paint, and oil will have high emissivity with values above 0.8, and shiny metals will have very low emissivity with values less than 0.2. Think about getting into your car that has been sitting out in the sun. If you reach your hand toward the dashboard, you will feel the heat being radiated from the vinyl or leather surface because those materials have high emissivity, which means they radiate heat efficiently. But if you reach for the shiny chrome-plated steel belt buckle, you may burn your fingers when you touch it. That is because that material has a low emissivity and does not radiate their heat very efficiently. You should be selecting an appropriate emissivity for the target you are measuring. Your camera has a built-in table of emissivity value settings to help with this. It's important to remember it is the material on the surface of the target we are concerned about, not the materials and the components beneath the surface. If safe to do so, you can use a piece of common 0.95 emissivity 3M electrical tape applied to a surface to compare your readings to a known emissivity location, or to measure the emissivity and reflectivity of the surface as is taught in a Level 1 thermography course. Direct versus indirect temperature measurement. A direct temperature measurement is when we have a direct line of sight on the object that is generating the heat. An indirect temperature measurement is when we have a heat-generating object and it's hidden behind something, preventing us from having that direct line of sight. An example might be a faulty bearing that is heating up due to friction. If we can see the outer surface of the bearing, that is a direct measurement. If the bearing is enclosed by a safety shroud and we cannot measure its surface directly, that is an indirect temperature measurement. This concept is important because risk assessment based on temperature rise is normally based on direct temperature measurements. Effect of fans on temperature measurement. Fans move air across surfaces. When that happens, heat is conducted from the object surface to the cooler air molecules, which are then stripped away by the air movement. The net effect is that fans really do work to cool the surface, and this will show up in the temperature measurement. Therefore, it's important that when performing thermography on an asset, it is always operating in the same way, and it's best if any fan cooling the object is subjected to is turned off temporarily while the inspection is being performed. Why equipment needs to be in normal operation. Equipment being inspected must be in operation during the inspection. Whether we are looking for signs of electrical resistance or mechanical friction, these signs will not be there if the equipment is not under load or not moving. Mechanical equipment such as belts, bearings, pumps, motors, etc. should be running for at least 1 hour prior to inspection.